Imagine you have a row of Lego blocks, each block is a matrix. When you press two blocks together you have to spend some effort, the number of scalar multiplications. The effort depends on the size of the two blocks. If the first block is P times Q and the second is Q times R, you need P times Q times R little operations. The matrix chain multiplication problem asks, given matrices A1, A2, up to a n with dimensions P0 times P1, P1 times P2, up to Pn minus 1 times Pn, how should you put parentheses so that the total number of scalar multiplications is as small as possible? In the real world, this is like a factory that needs to multiply several transformation matrices to move a 3D object. Multiplying them in the wrong order can waste a lot of CPU time, just as joining two very long ropes before cutting them costs more than cutting first, and then joining the short pieces. Formally, we want a parenthesization of the product A1, A2 up to a n that minimizes the sum of costs for every multiplication step. The simplest way to solve the problem is to try every possible way to split the chain, just like trying every way to cut a chocolate bar into pieces. A recursive function cost ij returns the cheapest cost for multiplying matrices, a I through a j. It works by choosing a split point k where I is less than or equal to k and k is less than j, recursively solving the left part cost ik and the right part cost k plus 1j, and then adding the cost of finally multiplying the two resulting matrices, p sub I minus 1 times p sub k times p sub j. The recursion looks like cost ij equals 0 if I equals j, cost ij equals the minimum over I less than or equal to k less than j of cost ik plus cost k plus 1j plus p sub I minus 1 times p sub k times p sub j. If you draw the recursion tree for n equals 4, you will see many identical subcalls, such as cost 2, 3 appearing over and over. Those repeated calls are overlapping subproblems. The same smaller problem is solved many times, which makes the naive recursion exponentially slow, about big O of 2 to the n. Dynamic programming works because the problem has optimal substructure. The best way to multiply a long chain includes the best ways to multiply its pieces. Suppose the optimal parenthesization of a I to a j splits between a k and a k plus 1. Then the cost of the whole chain is the sum of three parts. Number 1, the cheapest way to multiply the left piece, m sub I sub k. Number 2, the cheapest way to multiply the right piece, m sub k plus 1 sub j. Number 3, the cost of finally multiplying the two results, which is p sub I minus 1 times p sub k times p sub j. Therefore, we can write the recurrence. M sub I sub j equals 0 if I equals j. M sub I sub j equals the minimum over I less than or equal to k less than j of open parenthesis. M sub I sub k plus m sub k plus 1 sub j plus p sub I minus 1 times p sub k times p sub j close parenthesis otherwise. The matrix M stores the minimum number of scalar multiplications for every subchain. The extra matrix S, sometimes called split, remembers which k gave the minimum, so we can later rebuild the parentheses. Explanation: to fill the table without recursion, we use a bottom-up approach. We create a two-dimensional array m bracket 1 to n bracket 1 to n, and set m bracket I equals 0, because a single matrix costs nothing to multiply. Then we consider chains of length L equals 2, 3, up to n. For each length we slide a window j equals I plus L minus 1 across the chain, and compute m bracket I bracket j using the recurrence, trying every possible split k. For I equals 1 to n colon m bracket I equals 0. For L equals 2 to n colon comment chain length. For I equals 1 to n minus L plus 1 colon j equals I plus L minus 1. M bracket I bracket j equals infinity. For k equals I to j minus 1 colon q equals m bracket I bracket k plus m bracket k plus 1 bracket j plus p sub I minus 1 times p sub k times p sub j if q less than m bracket I bracket j colon m bracket I bracket j equals QNS bracket I bracket j equals k comment. Remember split point. The filling order, increasing L, guarantees that when we need m bracket I bracket k or m bracket k plus 1 bracket j, they have already been computed, just like building a tower floor by floor. The table M finally holds the optimal cost at M bracket 1 bracket N. The naive exhaustive search tries every parenthesization. The number of ways to parenthesize N matrices is the Catalan number C sub N minus 1 approximately 4 to the N divided by N to the 3/2 times square root of pi, which grows exponentially. Hence the exhaustive method needs big O of C sub N minus 1 approximately big O of 4 to the N time. Impossible for N larger than about 15. Dynamic programming reduces this dramatically. We fill an N by N table, and for each cell we examine at most N split points. The total work is summation from L equals 2 to N of N minus L plus 1 times L minus 1 equals big O of N cubed. So the time complexity is theta of N cubed. The space complexity is theta of N squared for the tables M and S. For typical values N less than or equal to 500, this is easily affordable on modern computers, while the exponential method is not. In short, DP turns an impossible exponential problem into a manageable cubic one. Explanation: after the tables are filled, we still need to know how to place the parentheses. The matrix S sub ij tells us the best split point K for the subchain AI to a J. A simple recursive routine can read S and print the parentheses. Print parenthesis ij. If I equals J, output A plus I. Else, output open parenthesis. Print parenthesis is sub ij. Print parenthesis S sub ij plus 1j. Output close parenthesis. Calling print parenthesis, 1n yields the optimal parenthesization. For example, open open a 1 open a 2, a 3 close close, open open a 4 a 5 close, a 6 close. The recursion uses the stored split points, so the construction is O of n time. If you prefer an iterative version, you can push intervals onto a stack and pop them using S to decide the next interval. But the idea stays the same. The DP algorithm not only gives the minimal cost, it also records enough information to rebuild the actual sequence of multiplications. The key insight is that the DP algorithm not only gives the minimal cost, it also records enough information to rebuild the actual sequence of multiplications. When you code this algorithm, watch out for a few common issues. Indexing: most textbooks number matrices from 1, but many programming languages use zero-based arrays. Keep P sub the dimension array 1 element longer than the number of matrices and adjust the indices consistently. Integer overflow: the product P sub I minus 1 times P sub K times P sub J can exceed 32-bit range even for modest dimensions. Use 64-bit long in C++, long in Java, or arbitrary precision integers. Initialization: set M sub I sub J to a very large value, for example INF, before the inner loop. Otherwise, a stray small value will corrupt the minimum. Memory usage: the two n by n tables take O of n squared space. For very large n, you can store only the upper triangle or use a one-dimensional array with clever indexing. But for most practical sizes, this is unnecessary. Reconstruction order: the recursive printing function can cause deep recursion for large n if the call stack might overflow. Replace recursion with an explicit stack. Zero-dimension matrices: the formulation assumes all dimensions are positive. Guard against empty input or a chain of length 0. Matrix chain multiplication is not just a textbook puzzle. It appears in many real systems. SQL query optimization: a database often has to join several tables. Each join can be thought of as multiplying two result matrices. The optimizer uses a DP similar to matrix chain to find the join order that minimizes intermediate row counts, which reduces I/O and CPU time. Computer graphics: to render a 3D scene, you may apply a sequence of transformations. Scale, rotate, translate. Multiplying the transformation matrices once in the best order yields the same final effect but with fewer arithmetic operations, which matters for real-time games. Scientific computing: in tensor contractions or chaining linear solves, the order of matrix multiplications can dominate runtime. High-performance libraries, for example BLAS, LAPSCK, often embed matrix chain DP to decide the evaluation order of complex expressions. Signal processing: filters can be represented as matrices. Chaining multiple filters benefits from optimal multiplication order. In all these domains, the goal is the same. Reduce the total number of elementary operations, which translates directly into faster programs, lower energy consumption, and the ability to handle larger data sets.